So instead of graphing this function around a unit circle or in a Cartesian plane, we're going to graph it like we saw it in the 12 basic functions. Remember when we did the 12 basic functions, it looked like a wave? We're going to figure out how, why, and all of those things about it. I think it would be very helpful if you have your unit circle page to have it open. Just like grab your unit circle page out of your notes and have it with you so you can very quickly see where I'm getting the values from for all of these different things. Because we want to graph not in a circle anymore, but on an XY plane. Now my x-axis is going to be counted in radians. If you notice, first things first, that I don't have my x-axis labeled 1, 2, 3, 4, 5. I have it labeled in the radian measurements that are important to us. So our graph here is pi over 6, pi over 3, pi over 2, 2 pi over 3, you can read it. Okay, so it's going to be done in radians because it makes more sense this way since the unit circle really is done in degrees or radians. So if we're looking at our periodic functions means it just repeats over and over again, or it waves, or it oscillates back and forth. Off of your unit circle, we're just going to fill in what the sign of 1 is, or sorry, the sign of 0 is. So look at your unit circle. Remember, sine is the second coordinate around the unit circle. What is the second coordinate at 0? So look at 0 on your unit circle. It's 0. Okay, so 0 is going to go with 0. Great. What is partnered, or what is the second coordinate at pi over 6? 1/2. Jump all the way to pi over 2. What is the second coordinate there? 1. Move again to 5 pi over 6. It's kind of far. 1/2. Go to pi. 0. Go to 7 pi over 6. Negative 1/2. 3 pi over 2. And 11 pi over 6. And then 2 pi. 0. Do you see a pattern here?
Yes.
Yeah. So our graph, when we graph it, is going to look something like this. And we're just doing one period or one wave of it. We have 0, 0. We have pi over 6, comma 1/2. Pi over 2, comma 1. 5 pi over 6, comma 1/2. Pi, comma 0. Pi over 6, comma negative 1/2. 3 pi over 2, comma negative 1. 11 pi over 6, comma negative 1/2. And 2 pi, comma 0. Look at that shape when we graph all of those things. What is that? A squiggly line. Yeah, it is a sine wave. So if we play connect the dots, you have a question? Yes, what's up?
Where did you get the values from again?
Oh, from the table.
No, I mean like from the...
Oh, the second coordinate. Remember, on our unit circle, all of the coordinate points are cosine of theta, comma sine of theta. So if we looked at just the second coordinate around my unit circle for each of those radian values, I got this table. So look, all of the like coordinate pairs should be the y value essentially. It is Monday. So when we play connect the dots here, we're going to get a curve. Now do your best to draw an actual curve and not like a bunch of sticks that create the sine curve. This is called one period of a sine curve. One wave, you can think of it as a sine curve, but we call them periods because they're the like amount of time it takes for it to repeat itself, called a period. Now that's the basics of a sine function. Now obviously this would extend out from negative infinity to positive infinity, continually going up and down, up and down, up and down, back and forth. We learned a lot of things about sine and cosine back in like September when we did the 12 basic functions. So let's remember some of those things and add in a little bit more. We didn't discuss the first two blanks here in September, but we can talk about where the period starts and period ends for the specific graph that we showed here. A period for us would start at the coordinate point 0, 0, because that's where we first started graphing. Where did it end? What x value did I stop graphing at? 2 pi, and what y value was I at? 0. Okay, great. So we have kind of this idea of one clean period for this graph. Starts at 0, ends at 2 pi, starting and stopping both at the value 0. What is the maximum value? What is the minimum value? -1. Great. So my domain and my range kind of come from, well, my domain for this graph, because it's not a rational, it's not a logarithm, it's not a square root, is all real numbers. Obviously, we didn't graph all of it. We just graphed one period of it, starting at 0 and going to 2 pi. But my range comes from the maximum and minimum. But when I write my range, instead of parentheses, what am I going to put on the outside of it? Brackets, because it actually touches -1 and 1. Ooh, symmetry. Do we remember the two types of symmetry that these sine and cosines would have? Even versus odd. Which one was sine? It is the one that goes through the origin. That's your big hint on which one it is. Origin. Odd. If you remember, odd functions are the ones where you can put a pin in the origin and rotate it around itself, and it would land back right on the same picture. Obviously, not the graph we did, because we only drew one period in the positive direction, but had we had an extra curve on the other side, you could almost like rotate it around, and it would land on itself. So it's an odd function, as opposed to even, which is the one that can fold flat. Its boundedness is that it is actually bounded above and below. We would just call that bounded. It has a maximum and a minimum. And then we're going to list out some of the zeros. The zeros that I currently see, remember zeros are x-intercepts, are at the value 0, pi, and 2 pi. But if I were to keep this pattern going, because it doesn't just stop at 2 pi, it's going to continually wave back and forth, right? So we can write what's called a general solution, or a general formula for the zeros, by taking the first 0 that you found, which was 0, and adding the distance it takes to get from 0 to 0. So how far did it take me on the x-axis to go from the first 0 to the second? What is this distance? Pi. So I'm going to add pi times a multiple that I was just going to name k. So depending on what k you plug in, you're going to find a 0 at that point for this graph, because every time there's a multiple of pi, it's going to cross the x-axis. Great. That's sine. And when we graph it linearly, graph it on a xy coordinate grid like this instead of angularly in a unit circle, this is what it looks like. Sound good? Okay, great. Let's do cosine. So we're going to do the exact same thing, but with cosine. Now, if you notice, I did change the values in the table. We were using multiples of pi over 6, so multiples of 30 degrees to graph cosine or sine. This one is multiples of pi over 3 or 60 degrees. So again, looking around your unit circle, what is the cosine of 0? 1. What is the cosine of pi over 3? 1/2. What is the cosine of pi over 2? 0. What is the cosine of 3 pi over 2? I mean, what? 2 pi over 3. -1. Do you kind of see what's happening here? What do you guess is going to be next? Don't even look at your unit circle. -1, and then? Not yet. -1/2, and then? And then? And then? 1 meets back where it starts. So we can kind of see the pattern. We got all these numbers from your unit circle, so if you're like, what? Go back to look at your unit circle. It's the first coordinate, because cosine is the first coordinate. We plot these points. We have 0, 1. This one does not start at the origin. Pi over 3, 1/2. Pi over 2, 0. 2 pi over 3, -1/2. Pi, -1. Then -1/2. Then 0. You guys can plot points. And once you're done, you have one period of the cosine function. Now, it looks weird when you just graph one period specifically between 0 and 2 pi because of the shape that it is. You're very tempted to draw this like a quadratic. Remember, it is not a quadratic. This is a cosine function. So when I play connect the dots, I don't go up at the ends. I know that it's eventually going to turn back down to complete the shape. So I would graph it something like that. Where after the points that I plotted on here, if we had done more, it would have curved back down. Between 0 and 2 pi doesn't look as cool as sine, but it eventually does when you graph more than one period of it. Okay, let's go over the same basic info for cosine. For this specific period that we graphed, what is the coordinate point that starts it? 0, 1. Great. What is the specific coordinate that stops this period? 2 pi, 1. Great, so things we notice. One period for cosine and one period for sine are the same length. It took me 2 pi to finish the shape one time. But sine started at 0 and ended at 0. Cosine started at 1 and ended at 1. Those are some things to notice. What's the maximum value? 1. What's the minimum value? Ah, that sounds familiar. Great. The domain, again, is from negative infinity to infinity. We didn't graph that far, obviously. And the range is still between that minimum value of -1 and the maximum value of 1. It's got those biggest and lowest values. What kind of symmetry does this one have? Even. Remember, even is the kind of symmetry where if you folded it along the x-axis, the graph would look the exact same. Obviously hard to tell when we just graph one period of it, but if we were to continue, so it looks like this, it like kind of makes the same shape. I'm using my hands, you can't really see what I'm doing here, but it would fold and be right on top of itself, so it is even. It is still bounded because it has a highest and a lowest value, but the formula for the zeros is going to be different this time. When we look at the zeros here, what's the first time you run into an x-intercept? Pi over 2. What's the next time you run into an x-intercept? Great. So we're going to use that information to create my little formula. The formula for the general solution is the first time you see a 0, which for cosine is pi over 2, plus the distance it takes for another one to show up. Not as easy because we're not starting at 0, but what is the distance between this 0 and this 0? 2 pi over 2, which reduces to pi. So we would have to travel pi away from the first 0 to find the next one. And so we just keep multiplying that by some value k. And we're going to keep finding the different zeros. So again, if you notice, and this is going to look better whenever I have more than one period graphed at a time, sine and cosine look very similar. Do you agree? Yeah. How are they related? Like, how could you get them to look the same? Just so you know, and I think when I printed, no, I didn't. Did I put this on here? Sine is the one that is dashed, and cosine is the one that's solid on your paper. I know mine are color-coded, so you can see a difference, but yours are not. So if I started with the sine function, the dashed graph, how would I get to cosine? What kind of transformation would I have to apply to it? Horizontal, hold on to that idea. What is that called when you move side to side? Starts with a T. Translation. So if we were to perform a horizontal translation to this graph, and now how far would I need to translate it to make this graph look like this graph? Let me do that again so you can see what I'm doing because you're all writing. It's fine. I started here, and then it got here. How much did I horizontally translate it? Not 1/2, but close. Pi over 2. So if we add or subtract pi over 2, a horizontal translation either direction, we're going to take cosine and make sine, or take sine and make cosine, which is cool but also confusing. Because when you have horizontal translations, you don't know which graph you've been using the whole time, which will come back to haunt us after lunch when we start graphing them more. We can apply a bunch of the transformations that we've learned about since Algebra 1 to sine and cosine functions. We're going to assign it normal names and then new names for periodic functions, so just hang on with me. Whenever we would have a number in front of the function itself, so something like here, like 5 sine or 3 cosine, that would provide us with a vertical stretch or shrink. So again, it's exactly like it was for all other functions. If you multiply a number in front of it, it's going to vertically stretch it or vertically shrink it. Does anyone remember what happens when you multiply a number on the inside? Horizontal stretch and shrink. Now with periodic functions, especially sine and cosine, the horizontal stretches and shrinks are actually the best example of those two words. And we're going to talk about that again later. They're probably the function where it's the easiest to notice a horizontal stretch or shrink and to appreciate what it's doing. If we were to be adding or subtracting a number on the inside of the function itself, does anyone remember what that would be called?
Horizontal translation.
Horizontal translation. Ooh, didn't fit that word in the box. And last but not least, if you have a number added or subtracted at the end of the function itself, what was that called? Vertical translation. Now, on this little document right here, I didn't leave a spot for our reflections, but your reflection would also be attached to either A or B. So your reflection over the x-axis would be a negative sign attached to A, and reflection over the y-axis would be attached to B. We're not going to see reflections over the y's. I didn't pick any examples with it, but you will see some where it's reflected over the x, but that's pretty easy to see because we reflect it. Now, all of these things have separate names when it comes to periodic functions. So we need to go over the new vocabulary for sinusoids, which is what these periodic functions are called. Now, something that seems pretty obvious, you have a center line to each of these sinusoids. This line represents the middle of the wave as well as the displacement of the graph. So our center line is literally for anything that's not transformed is the x-axis because it's the center of the wave. Knowing your center line is super important for graphing because it gives us our, what you can think of as baseline or center line. It's named really well. The period of a function is represented by capital P, not lowercase p, capital P. It is the time that it takes for a function to repeat itself. So if we looked at this sine curve that you have here, I know it's sine because it goes through 0. The next time that this shape, like it goes up, it goes down, it comes back up, and then it would start over, that distance is the period. So you would need to look for a repeating shape to decide that that is one period. So for this particular graph, if it starts at 0 and ends at 8 pi, then you'd say that the period is equal to 8 pi. I know those numbers are terribly small to see, but however long it takes for the shape to repeat itself is the period. Now there is a formula for period that you will need to know. The formula for period is 2 pi divided by b. Where do you think I got the b from?
The time it takes?
That would be the period. That's the time it takes. Where else on this paper do we see a b? Yeah, up there. This value here, your horizontal stretch or shrink number, actually affects the period of your graph because it's going to change how long it takes for the graph to repeat itself. General solution we've kind of talked about before. The general solution is a formula for all the zeros of the entire wave from negative infinity to infinity. The formula was x equal to the first 0 plus k times what we're going to call the period divided by 2. So however long it takes for it to repeat, divide by 2, and that's what you would multiply by k. Now, amplitude is probably a word you've only used in reference to music, but amplitude is a mathematical idea. Is why you call amplitude in music, because music makes sound waves, and these are waves. Amplitude is represented by absolute value of A. Where do you think I got the A from?
The stretch and shrink.
the vertical stretch and shrink. It is the distance from the center line to the maximum or minimum. So if you looked at our center line and went to our maximum, this would be my amplitude. But what's cool is since we're doing the absolute value of the amplitude of the A to find the amplitude, you can look either on the positive side of the center line or on the negative side of the center line to decide what the amplitude is. Now I'm lazy, I'm not going to write the word amplitude out probably ever again. I'm going to use amp. Is everybody okay with that? Mm-hmm. Great. But the amplitude is just the distance from the center line to the maximum or minimum. The x increment is not something that you would necessarily see on a graph. It's not like something you can point at and be like, that is the x increment. But it is a labeling system for the x-axis to allow us to graph by hand way easier. The x increment is the period, which I'll actually write out all the way, divided by 4. It's not going to make sense why we need that until we start graphing functions themselves, but the x increment, 100% you need anytime I ask you to hand graph a sine or cosine function. Even if it doesn't ask for it, you find it. So maybe put a little star next to this. It's super important. You need that. Now, what's called a phase shift is represented by the letter C. Where do you think I got the C from? Horizontal translation. It is the horizontal translation of the graph. In sinusoids, we call them phase shifts. So again, sine and cosine are just phase shifts of each other, because if we just move one a certain distance away, it creates the other graph itself. But you would just look for how far away the original graph is to the one that is graphed, so from the dashed to the solid line essentially, and that is your phase shift. So this graph has been shifted pi over 4 to the right. So you'd see a minus pi over 4 in that formula. Few more vocabulary words. There's a lot of new vocabulary when it comes to sinusoids. We can take all of these vocabulary words that we just saw and change how we wrote these words. Instead of vertical stretch or shrink, the word that we're going to use to discuss that in regards to sinusoids is the amplitude. It's the same thing. I'm still working on the vertical stretch and shrink, but we're going to call it amplitude. Instead of calling it the horizontal stretch or shrink, we're going to refer to the B in regards to the period or the frequency, because that's the useful version, or why you would ever look at the horizontal stretch or shrink for one of these graphs. For horizontal translation, we're going to call that phase shift. But like I said, I'm lazy. I'm going to call that PS from here on out, phase shift. Is that okay with everybody? You can also shorten it like that. And then vertical translation, I'm going to call it a displacement now, but I'm also going to shorten that one to DISP because that's way too long. So those are the words I'm going to be using. I'm still just talking about the things we've been studying since Algebra 1. They just have new vocabulary when it comes to sinusoids. Sound good? I'm waiting. Because we're going to get into actually graphing them ourselves. Now, obviously, you can see that I graphed one for you on your notes, sort of. I didn't finish it. But we're going to talk about why I did what I did and what I'm expecting of you every time that you graph a function, including displacement. Displacement is the vertical translation of the graph, so pretty obviously it is the letter D. D for displacement is what I like to think. But it's truly just, if it's positive, the graph moved up. If it's negative, the graph moved down. It is your vertical translation, but we call it a displacement. I find it easiest to notice the displacement either comparing maximum and minimums or zeros. So specifically, the fact that this has a 0 at 0, 0, and then it is shifted up how many units? 2. So it has a displacement of 2. Literally, it works exactly like a vertical translation, but we're going to call it displacement. Now, another word you've probably only thought about in regards to sound, which again, sound waves. Oh, look, waves, is called frequency. Frequency is how often the wave happens, the complete wave happens, compared to the parent wave. So what we would do is we use the reciprocal of the period, 1 divided by the period, or b divided by 2 pi, to find the frequency. But really, as long as I will ask you for the frequency occasionally, just flip over the period. But for the most part, you just need to know if you have a high frequency or a low frequency graph. So if you look, the dashed line here is the original parent function, just a normal sine curve. So do you notice that in the time it takes to complete a full sine curve, so from 0 to 2 pi, we have 1, 2, 3, 4, 5 entire sine waves. So this would have a frequency of 5 because it had 5 waves in the time it should have taken to just have 1. On the other hand, here's a normal period in the dashed line. I only got halfway through the low frequency. So this one takes 2 entire periods for it to work. So it'd have a frequency of a half. So you either have high frequency or low frequency transformations of the sine or cosine function. So putting this back all together on the other page. Okay. In number 1, we want to list the amplitude in the period, then use the correct x increment to graph at least one period of the function on the interval from -2 pi to 2 pi. And be sure to label the scale of each axis. This is kind of the basics of what kind of question I'm going to be asking you to do on homeworks and on quizzes and on tests. Okay? So first things first, when I look at one of these problems, the first thing I do is label A, B, C, and D. My transformation letters, aka the things that tell me all the answers in sinusoids. A is 2 because there's a 2 in front of sine. B is 1 because there's a 1 next to this x right now. Then I don't have anything added or subtracted inside or outside, so C and D are both 0. If I find the amplitude, the formula for amplitude was square root of A. Cool. Square root of A means I'm taking the square root of 2. That's 2. That means that my graph doesn't go to 1 and -1. It goes to 2 and -2. That's the amplitude. We've stretched it out. That's how high or how low it should go. The period formula is 2 pi over b, and b is 1, so it's 2 pi over 1, which is 2 pi. That means that a complete curve should happen every 2 pi. The last thing I need, even if it doesn't ask me for it, is the x increment, which is just the period divided by 4. So I do 2 pi divided by 4, that's pi over 2. Pi over 2 is what I label my graph with. Don't go to pi over 6, don't go to pi over 3, don't do extra. Only label with your x increment. So if you notice on your graph, we have 0, we had pi over 2. We would have 2 pi over 2, but that's pi. 3 pi over 2, 4 pi's over 2, that's 2 pi. And I do the same thing negatively. I've labeled my x-axis, then I'm good to go. I also labeled my y-axis to have an amplitude of 2. Okay. Here's what I need us to know and to maybe write down on the side, somewhere where you're going to see it and remember it. Sine and cosine have patterns when you've used the x increment. The x increment pattern for sine, if you've done the correct x increment, is the following. Center line, maximum. Center line, minimum. Repeat. Center, max, center, min, center, max, center, min. Just so that we can all write this down. Cosine is going to be similar, just different. It starts at a maximum, then goes to the center, then goes to the minimum, then goes to the center. Center, max, center, min is always the pattern. Sine starts at a center, cosine starts at a max. Here's why that's helpful to have that pattern. Center up, center down, center up, center down. It's going to wave back and forth. Because we have labeled our graph with the maximums, the center line, and my x increment, you start at the center. The first time I get to an x increment, I go to the maximum. The next x increment number, center. Then minimum, then center. You can finish the pattern going the other way. Center, center, min, center, max, center. If I were to keep going, that pattern would continue. Once I've got my dots there, though, I can play connect the dots. And we do a couple, oh, that was terrible. Let me try again. Nope, also not good. Drawing curves is hard. That'll do. A couple checks you do for yourself before you call a problem done. Number one, is my amplitude correct? Is my amplitude 2? Yes, okay, great. Does it take 2 pi distance for me to finish one wave? If I start at 0 and get to 2 pi, did I finish one wave, up and down? Great. If you've done that, then you've graphed it correctly. Your x increment will change, and it will change how many waves you get in 2 pi. But finding that x increment means the pattern works. Center up, center down, center up, center down. Don't have to do anything about in-betweens. That's the pattern. Yes?
What do you have to check again to make sure it's...
I always check amplitude and period.
Okay.
Because if those two are good, then most likely everything else is good. That's your quick, and they're quick to check. Like, is it the right height? Is it the right distance? Okay, seems pretty good. Can we try one together? Okay, because it's not going to make sense till we try some. And we're going to be graphing. That's kind of the goal here. If we want to graph y equal to cosine of 2x, I want to label A, B, C, and D first of all, just because that's helpful to have. What is A? 1. What is B? 2. What is C? And D? Okay, great. Is anybody lost where we got these numbers from? Because we just kind of went for it. Before today, you would have said that this cosine graph has a horizontal shrink by a factor of 1/2. You are correct, but that means something different for us with sinusoids. If we're finding the amplitude is just square root, absolute value of A. So I'm finding the absolute value of 1, which very obviously is 1. So the height of my graph will only go up to 1. So when you draw a tick mark on your graph for your amplitude, you only have to label it 1 and -1. Great. Yes, it can be giant. As long as it is labeled, you have graphed it correctly. Because notice, I basically used the same distance for 1 in examples down here as I did for 2 in the example up there. That's okay, it's labeled. You know what it stands for. As long as you label your stuff, you'll be fine. Okay. Let's find the period. The formula for period is 2 pi divided by b, but b in this case is 2. So I have 2 pi divided by 2, otherwise known as pi. Great, so my wave, my sine curve, cosine curve should completely finish in pi distance, not 2 pi. To graph it, we find our x increment every time. X increment is just your period divided by 4, which is going to be pi, that we just found, divided by 4. That means when I label my graph, I want to label every pi over 4 distance, all the way from -2 pi to 2 pi, because it will allow me to follow the pattern. Okay. Put your pencils down for a second and just watch what I do, because this is weird if you're thinking too hard while I do it. Start on the positive side, it's just easier. If this is 2 pi, then what's this, like halfway in between? Pi. But I'm going to write it with a denominator of 4, because I have an x increment of pi over 4, which means there should be 1, 2, 3 pi's before the 4 pi. This is 1 pi over 4, 2 pi over 4, 3 pi over 4. Do you see what I'm doing? Then we have 4, we'd have 5, we'd have 6, we'd have 7, and we'd have 8 pi over 4, which is 2. Yes, a lot of those would reduce. If you would like to reduce them, you can. Probably graphs I give you would have it reduced, but for use, that's fine. We're going to go the opposite way, but once you've done all the hard work in one direction, you can do it in the other way because it's just opposite. Well, let me do it in the middle. Let me actually write it right. -4 pi over 4, so this is -1, -2, -3, -4, -5, ooh, doesn't fit, -6, and -7. Whew, labeling the axis. Take the labeling seriously. Because once you have it labeled correctly with the correct amplitude and x increment, you just follow the pattern. The pattern for cosine started where? Did it start at the center or at the top? Oh, we're all still labeling our stuff. I'll give you a second. Does cosine start at the origin or at the maximum? Maximum, which means at 0, I'm going to go ahead and plot 0, 1. I always like going the positive direction first when I'm graphing, just because that's easier. The pattern goes maximum, center, minimum, center. Every time I put a tick mark, I need to put a dot, which is why we chose a specific x increment for this graph. After center, I go to max, and then center, and then min, and then center, and then max. Then we go the opposite way. We started at max, going to the left, center, down, center, up, center line, minimum, center line, maximum. Once you've got all your dots, which there's a lot of dots, you can play connect the dots. And if you connect the dots correctly, it's going to look something like that. Oh my goodness, wild. The x increment that you choose allows you to graph easier. If you choose the wrong x increment, then the graph is all sorts of off. Now question, what are the two things I asked you to check once you've graphed?
Amplitude and frequency.
Amplitude and period, but yeah, period and frequency are very much related to each other, so that's good. So amplitude, is my amplitude 1?
Yes.
Yeah, from the center line to the maximum or from the center line to the minimum, I have labeled it 1. Great. Then I need to check the period. I said a whole curve should appear in pi. Okay, here's 0. Here's pi. Did I finish the cosine curve?
Yes.
Good, then we're done. The frequency tells me that there are 2 pi's for every normal pi, or 2 waves for every normal wave. So here's 1, here's 2. We've done 2 waves in the time it normally takes there to be 1 wave. It's a higher frequency graph. Comments, concerns, questions? No? Okay, let's try one to see if we can think of comments, concerns, questions. On the next page, I don't want you to necessarily do it all right now. I just want you to do all of the stuff on the side. See if you can do the amplitude, the period, the x increment, and maybe labeling. And I'll catch you up for everything else. Amplitude, period, x increment, and try labeling on your own. on my desk as well. So with this one, we should have noticed that the x increment is the period divided by 4. So 4 pi divided by 4. What is the x increment? What is my labeling system going to consist of? Just pi's. I don't have to do anything smaller or in between pi. This is nice. Here's how I would have labeled this graph for this problem. First of all, we know my amplitude is 3, so I need 3 little tick marks to show that it's going up or down 3. Cool. And then in between negative 2 pi and pi, the only things I have to label are pi. Don't get crazy. Here's pi, and here's negative pi. That's the entire x increment. I don't have to do anything in between that. We had to do pi over 4s earlier, so split it into 4 between 0 and pi. I don't have to do any of that. From here, we follow the pattern. The pattern for cosine, right, this is cosine, right? Yeah, was maximum, center, minimum, center, maximum. But since it's a reflection, instead of starting at the maximum, what am I going to start at? Minimum. So I'm going to actually start down here. But then the pattern continues. Minimum, center, maximum. Cool, done on that side. There was nothing else in between that I needed to plot. Then on the other side, since I'm at a minimum, I go center, and then I have to go to the maximum. Doesn't feel like we did enough, but that's it. We play connect the dots. This cosine curve looks like that. Feels weird. But we checked the 2 things that we need to check, which is amplitude and period. Did I label my amplitude to be 3? Good, because even though I kind of drew it ugly, but this is 3 down or 3 up. Cool, then the period we said would be 4 pi, which means I need to travel 4 pi distances to finish one curve. Here's one entire curve. How long did it take me to do that? From negative 2 pi to 2 pi, which is 4 pi's. In a distance. Looks like we didn't do enough, but that is correct. The x increment allows me to just do the dots that I'm going to connect on those coordinate points, those x-axis tick marks.
Is there not a tangent graph?
There is. We are going to learn today only about sine and cosine. The next one we're going to learn about is actually cosecant and secant, and then we'll get to tangent because he's weird. No offense, tangent, but offense. Okay, do we have any questions about graphing, like the basics for sine and cosine besides your... Okay, so we've graphed them with different characteristics, but we can also write them with different characteristics. So question or example number 2 says, write a cosine function whose amplitude is 5 and whose period is pi over 3. Amplitude part, way easy. This number for the amplitude goes where in my formula? In the front, because the amplitude is A. So I'm going to have the amplitude being equal to 5, which really means that my A value is either 5 or negative 5, but it didn't tell us that this has a reflection in the x-axis, so we're not going to use the negative version. Technically, that's an option because absolute value means I can either have the negative or positive version, but it doesn't say to reflect it, so we ignore. It tells me that the period is pi over 3. But I don't plug the numbers pi over 3 into the formula. What number would I had I been getting to use in the period? By b, yeah. So we need a b value to plug in. So we know that the period is pi over 3, but we also know that period is 2 pi over b. Well, that's a proportion that I can solve because I only have one unknown variable, that's b. Yeah. So 3 times 2 pi is 6 pi. I'm doing the butterfly method. And then b times pi is b pi. Divide by divide by pi. Your b value is 6. So when we put that together, literally all it is y equal to 5 cosine of 6x. Now, I like putting my function, like the 6x in parentheses. They're not necessary. Like, obviously, the questions that we did earlier didn't have parentheses around, bless you, around their b value necessarily. I like putting them. It's much clearer what's inside, what's outside when you have them. But that's it. Did we understand how I found the b value? We set it equal to 2 pi over b, which is the formula, and then we can solve for b. Cool? Okay, we're gonna kick it up a notch in graphing. Are you ready? Because now, not only are we having an amplitude and a frequency or a period, we're going to add in some phase shifts and some displacements. So now we're going to have some C and D values here. So if we look at this first example, which I've done most of the work for you again, we have y equal to -4 sine of x plus 2. A would be -4, so we notice that that's a reflection. B would be 1, C would be 0, and D would be 2. This is why it would be helpful to have parentheses, because that's like kind of confusing. If you truly had your parentheses around x, it would be very obvious that plus 2 was a displacement and not a phase shift, but that's why I put them. They're not technically necessary. My amplitude is 4. My period would be 2 pi divided by 1, so that's 2 pi. 2 pi divided by 4 for my x increment means that my tick marks are going to represent pi over 2's. There is no phase shift because the C value is 0. And my displacement is that the entire graph is shifted up 2, which means that my center line, which I like to draw as a dashed line when it's not the x-axis, has moved up to 2. That's my center for when I'm doing the center max, center min stuff. Meaning my maximum value is not at 4, even though my amplitude is 4. Why is my maximum value at 6?
Because it went up.
It's already starting at 2, then it goes up 4. So my maximum is at 6. What's my minimum at? -2, because it starts at 2 and then goes down 4. So when you graph these with displacements, make sure you know where your center line is so that you don't accidentally graph it incorrectly or crooked. But after that, the pattern still remains. For sine, we start at the center. We went down because this is a reflection, so instead of going up, we go down to the lowest, and then center, making sure it's actually center and not accidentally the x-axis, and then max, and then center. Now we're only doing one period, so I'm going to be graphing just from 0 to 2 pi here, not in the negatives, just because that's what I chose to do here. It doesn't say I have to go from a certain value to a certain value. But there we go. There's one period of my graph that has an amplitude of 4, is a reflection over the x-axis, and has a displacement of 2. So I've shifted it up 2, stretched it out 4, and that's it. And reflected it. Questions before we go to B? Okay, let's try this one together. I always like to start with A, B, C's, and D's. What is A? 1, because there's no number in front of the word cosine. What is B? 1, because there's no number multiplied in front of x. What's C? Pi over 2. And what's D? 1. Okay. So we start by looking for the things we look for. Amplitude is first. Amplitude is the absolute value of A. So what's the amplitude of this graph? 1. We want the period. The period is 2 pi divided by B. So the period for this graph is still 2 pi, because 2 pi divided by 1 is 2 pi. I always want my x increment. Even though it doesn't ask for it, that's how you graph it. The x increment is the period divided by 4. So I'd be doing 2 pi divided by 4, which is pi over 2. That's what I'm labeling my axis with. my phase shift. There is a C value this time. The phase shift is pi over 2, but now we have to remember which direction, because sometimes that affects what it looks like. Since we had a plus sign up here, are we moving to the right or to the left? To the left. So we're going to be moving or phase shifting to the left 2 pi. Plus is always to the left and minus is always to the right. What is the displacement here? Which direction? Up. So it works just like all of the transformations did back when we were in Algebra 1 and Algebra 2, and earlier this year when we transformed graphs. But now we're applying it to waves, which makes it weird. Okay, when there are displacements, always start with that. My displacement of 1 means that my center of my graph is not at the x-axis. My center of my graph is going to be at the value 1. I like to draw a dashed line there, just so I remember that that is my center. Didn't really reach. Okay, great. Now I have my center line. I need my amplitude. From the center line, how much should it go up? 1, which means my maximum is going to be at the value 2, and my minimum is going to be at the value what? 0. Okay, great. Good check. Now we need to label our x-axis with my x increment. My x increment is pi over 2, which means that should be what each thing is labeled. Well, if I do this, that's normally pi, right? Because it's halfway between 0 and 2 pi. If I give it the denominator of 2, it's just 2 pi over 2. So I only have to do this. 1 pi over 2, then there's 2 pi over 2, and then there's 3 pi over 2. That's it. That's all of the labeling I'm going to have to do for this amount of space. Cool, then we get to the pattern, but this time we have a phase shift. So normally for cosine, the pattern is maximum, center, minimum, center. Oh, I don't know why I started writing that out. And then repeat, right? But we're moving it over pi over 2. That is 1 x increment, which means we're not doing this first one. Where am I going to start this cosine function? In the center, and then I'm going to go where? To the minimum, and then where? Center, and then where? Max, and then where? Center. Instead of, because normally cosine is max, center, max, center, min. Since it's phase shift 1 and that 1 matches the x increment, we're just skipping an x increment essentially in the pattern. Yes?
Could you just move the graph back or forth depending on how much the phase shift is?
Yes.
Instead of going by like the max, it could just be like minus pi over 2.
If they match. Yeah. Yes.
Is it possible for the phase shift to be bigger than pi over 2?
Yes.
So then I would move back like 3 or 4 spaces.
So if it was like a phase shift was 3 pi over 2, that's 3 of these. You would have skipped 1, 2, 3 of them and started there. Yes?
Question. So amplitude is always the number in front of cosine. Or behind it. It's the left and to the right of cosine.
The one in front of cosine is your vertical stretch and shrink called amplitude. So it changes your maximum and minimum. The one after it changes the period or how often the wave happens.
So A would be like 2 cosine parentheses and then B is the x inside the parentheses.
The number next to x, yes, which is 1. Yeah. Now here's something interesting about this graph. If we go ahead and play connect the dots here, what does this graph actually now look like? What normally starts at the center? Sine. Sine usually starts at the center and goes up, so it actually looks like a reflected sine graph, which is crazy, but that's because sine and cosine are just phase shifts of each other. So we ended up with a graph that looked very similar to sine because we phase shifted a cosine. These were great questions. I think we still need to do C together. I feel like the questions you guys just asked me, I'm going to answer a lot of them by doing the next example with you. Does that sound good? Okay. Start off the same way. We label A, B, C, D. What's A? 1. What's B? What's C? Pi over 3. What's D? Great. So is there a displacement of this graph? Is there a phase shift? Is there a vertical stretch? Did my amplitude change? Vertical stretch didn't happen. But is there a horizontal shrink? Yes, because my frequency is going to change. Okay, let's find all of those things actually. What is the amplitude? 1. Great. What is the period? Yeah, 2 pi over 3. Period is always 2 pi divided by b. Okay, my x increment is a weird one, so I'm going to do this one. I'll show a little bit of work on this. X increment is always the period divided by 4, which means we are doing 2 pi divided by 3 divided by 4. Yuck. This is not a keep, change, flip problem because there's no fraction in the denominator. This is straight up just a fraction problem. This is 2 pi divided by 3, and 4 is also in the denominator. So really, this is 2 pi divided by 12. And that reduces to pi over 6. So I'm going to be counting by pi over 6 for my x increment.
Does that switch to degrees, right?
Yes, but we're only doing radians as we go out. We don't do degrees on an XY graph. Okay, before you panic about labeling pi over 6, let's talk about the phase shift and displacement. What is the phase shift? Pi over 3 to the left, yeah. Ooh, but now my x increment and my phase shift don't match yet. Can I write pi over 3 with the denominator 6?
Yes.
Yeah, what is pi over 3 with the denominator 6? Great, so I'm going to skip how many things in my pattern before I start this thing? 2. So instead of going center up, center down, I'm going to not do the center and the up. I'm going to start center down, center up. That's what this means. Yes? Yes. And then last but not least, our displacement. We don't have one, so we would say none. No displacement. Ooh-wee, now we got to put this all on a graph. Are you ready? No, okay. Hardest part is your x increment, but if you just think about counting, it's really not that bad, which sounds silly to say. Here's my y-axis label, -1 and 1, because I know it's my amplitude and I have no phase shift. But then I need to label the x-axis, and this is when we take our time. In the middle would be pi, but to let it match the denominator, instead of just pi, I'm going to do 6 pi divided by 6. Okay, that kind of gives me a place to start. That means before it, I'm going to have 1 pi over 6, 2 pi's over 6. Yes, I know that reduces to pi over 3, but for now, we're not going to do that. 3 pi over 6. I'm about to run out of room. 4 pi over 6. 5 pi over 6. I do not care that they're evenly spaced. If they are labeled, that's fine, as evidenced by what I just did on the board here. We would then obviously have 7, and then 8 pi over 6, 9 pi over 6, 10 pi over 6, and 11 pi over 6. 12 pi over 6 is 2 pi, so I stop there. I do that process every time I do this. I always start with these 2 pi and 0, and then start with pi, because it's just easiest to start with those. And I'm telling you that because on your homework you won't have labeled graphs. So always start with 2 pi, go halfway for pi, then you can do your x increment. Okay? Great. We want to graph this thing now, but instead of the pattern being, I'll write it down. It's normally center max, center min, repeat center max, etc., etc., etc. But how many am I skipping this time? 2, because my phase shift is pi over 3, which is 2 pi's over 6. So I'm starting the same pattern, just 2 steps away. I'm starting at the center and then going to the minimum. And every single time I put a tick mark on this graph, there should be another coordinate point following that pattern. Then you get to play connect the dots. Ta-da! A sine graph. And I think we're going to stop right here for today. We're going to finish these notes next time. I feel like a lot of times when I don't finish notes, we don't come back to it, but we are going to finish these notes next time. So make sure you please bring them back. You should be able to do a good chunk of your homework, probably up into the second section. So don't wait until next time to start it.